Hey everyone, in this video we're going to learn how to define a function. In order to build up to that definition, we're going to start by looking at a couple of examples. The first example, match each number with all words that describe it. The numbers are 1, 2, 3, and 4. The types of numbers are odd, even, and prime. So we're going to draw an arrow from each number to all the words that describe that number. As a reminder, a prime number is any number whose only factors are itself and 1. Since 1 is part of that definition, 1 is not a prime number. So starting with 1, we can draw an arrow connecting that to odd, and that's the only arrow we can draw. 2, we can draw an arrow connecting 2 to even, and we can connect 2 to prime. Its only factors are 2 and 1. 3, we can draw an arrow connecting it to odd. We can also draw an arrow connecting it to prime. Its only factors are 3 and 1. 4, we can draw an arrow connecting it to even. So what we've done is created a relationship between the numbers 1, 2, 3, and 4 and the types of numbers odd, even, and prime. We can follow any of the arrows that we've drawn, starting with the number, follow the arrow, and output a word that describes that number. So now I want you to imagine that we have a machine that has the diagram that we just created. And when we input a number, 1, 2, 3, or 4, into that machine, it follows all of the arrows that we've drawn from that number and outputs any of the words that describe that number. So for instance, if we input 1 into the machine, it follows the blue arrow and it outputs the word odd. Have that machine input 2, it follows both green arrows and it outputs even and prime. We input 3, follows the red arrows, it outputs odd and prime. And we input 4, follows the purple arrow, outputs even. Okay, so our machine knows how to follow the arrows that we've drawn. So some inputs, 1 and 4, only output one word. 2 inputs, 2 and 3, output 2 words. So what happens to this relationship and to this machine if we remove the word prime? And that's exactly what we're going to do in the next example. So the same directions, the numbers are 1, 2, 3, and 4 still. The types of numbers are now only odd or even. Starting with 1, we can draw our arrow connecting it to odd. 2, we can draw our arrow connecting it to even. 3, an arrow connecting it to odd. And 4, connecting it to even. So we've created a relationship between the numbers and types of numbers again, but now we only have the word odd and even to connect to. So we notice we have less arrows. So we still have that same machine. It has this new diagram. So if we input 1, it follows the blue arrow, it outputs odd. Input 2 to the machine, follows the green arrow, outputs even. Input 3, it follows the red arrow, outputs odd. Input 4 follows the purple arrow, outputs even. So the biggest difference that we notice is when we input our numbers to the machine, now it only outputs one word, either odd or even. So we still have a relationship, but now it's a special type of relationship that only gives us one word for every number we input into that machine. Now we have a name for this special type of relationship, and it's called a function. So let's define both a relation and a function. A relation is a connection between two sets of information. So both of those two examples were relations. We created a connection between two sets of information. A relation can be represented by a set of ordered pairs. And what that means is we could take each of our arrows that connects a number to one of the words and write it as an ordered pair. For instance, we can write the ordered pair 1, odd. Right? We started at 1, we followed the arrow to the word odd. And we can do that for every arrow that we drew in both of the first two examples. A function is a relationship between two sets, x and y, in which each element of x is matched to one and only one element of y. And the key here that you should underline is one and only one. So the reason the first example, the first relation, was not a function is because if we input 2 into that machine, it gave us 2 outputs. It said even and prime, which means it went to 2 elements in the set y, not 1. But in our second relation, if we took any of those numbers, 1, 2, 3, or 4, input it into the machine would only output one word, odd or even. So x was the numbers, 1, 2, 3, and 4. Y were the type of numbers, odd or even. So every input mapped to only one output. And that's the way, in simpler terms, to think about a function. If you have an input, there's only one possible output. And in the examples that are going to follow, that's what we're looking for. Does each input have only one output? Now, 2 other words that we're going to see frequently throughout this unit are domain and range. Domain is the set of all inputs. So in our previous 2 examples, the domain were the numbers, 1, 2, 3, and 4. And we're going to think of those as x values. And the range is the set of all outputs. So in the first example, the range was odd, even, prime. In the second example, the range was odd, even. And we're going to think of those as the y values. Now that we've defined the difference between a relation and a function, but keeping in mind that a function is a relation, it's a specific type of relation, let's look at as many examples as we can to determine whether we have a relation or, more specifically, a function. Determine whether each of the following relations is a function. So they've given us 2 mappings, that's what we call these, from the numbers 5, 6, 7 to the numbers 10, 20, and 30. And you'll notice they label these as domain and range, so we get familiar with that vocabulary. Looking at our first mapping, input 5, output 10, input 6, output 30, input 7, output 20. So every input has only one output. So this is a function. Now they don't ask us to explain, but I think that's important. Every input has only one output. Looking at our next mapping, input 5, output 30. Input 6, output 10 and 20. So we can stop right there. Input one number, 6. We output 2 different numbers, 10 and 20. So this is not a function. And our reasoning is one input maps to 2 outputs. Okay, so the issue right there, well, not sure what happened. Issue here is 6. Right, we have 2 outputs for the input of 6. Next, they've represented the relations with a set of ordered pairs. So determine whether each set of ordered pairs is a function or not. So in a set of ordered pairs, just to remind ourselves, we want to think of the x values as the inputs. Let's fix that p as the inputs, and the y values as the outputs. So what we're looking for in the set of ordered pairs is that every input maps to only one output. So in the first order pair, -1 is the input, the output's +1. Inputs 3, output 0. Inputs -1, outputs 2. Inputs 1, outputs 8. So my suggestion is I would underline the x values so that we're focused only on the inputs. And what we should notice is that we have -1 as an input twice, and each time we get a different output. -1 outputs 1, -1 also outputs 2. So that means this is not a function. And our reason, again, they don't ask, but I think it's important. 1 input maps to 2 outputs. More specifically, the input of -1 maps to both 1 and 2. In our next example, -2 is the input, output is 4. 0 is the input, output is 4. 2 is the input, output is 4. 4 is the input, output is 4. So again, let's underline just the inputs so we're focused only on that. So we have no repetition of the inputs. So that means that we do have a function. Every input maps to only one output. So we'll write that every input maps to only one output. Now, some of you are probably looking at this set of ordered pairs and going, but the output's the same every time. In this set of ordered pairs, the output's always 4. That doesn't matter, right? As long as each input has one output. Could be the same every time, like in this example. Every input could output 4. That's okay, that's still a function. Now we have the relation represented as a table, so determine whether each table of values represents a function or not. So again, x is the input, right? So we can label that next to it. Input, output. Right? So input 1, output -7. Input 3, output 6. Input 5, output 0. Input 6, output -7. Input 10, output 11. So if we look at our inputs, every input maps to only one output. That means this is a function. Every input maps to only one output. And I know it's repetitive, but that's the idea. We really want to drill this definition into our mind. In the next table of values, again, x is the inputs, y is the outputs. So input -8, output -17. Input -5, output -12. Input -5, output -4. So we can stop there. What we notice is the input of -5 has 2 different outputs. Now, they're not always going to put it exactly next to each other in a table. They did us a favor here. But this is not a function. And the reason is one input maps to 2 outputs. Right? More specifically, the input of -5 maps to both -12 and -4. Explain why the following relation is not a function, then graph the points. So they're giving us a heads up that it's not a function. We just have to figure out why. So looking here, x are the inputs, y are the outputs. So 0 outputs 5, 1 outputs 1, 2 outputs 4, 3 outputs 2, 2 outputs 7. So what we notice is the input of 2 is repeated, and each time we get a different output. So explanation, the input of 2 maps to 2 different outputs. And I'll write them in parentheses, 4 and 7. So now they want us to graph the points. So 0, 5, 1, 2, 3, 4, 5, 1, 1, 2, 4, 3, 2, and 2, 7. So, the follow-up question is, what do you notice about the points that make the relation not a function? So what we notice is they both lie on the same vertical line. So they would be on the same vertical line. More specifically, the line x equals 2. Right, if we were to draw the line x equals 2, both those points would be on that line. Now, that's important because that's going to give us a way to tell if a graph is a function or not. And that's with the vertical line test. So the vertical line test for functions states that if every vertical line that can be drawn through the graph of a relation intersects the graph at one and only one point, then the relation is a function. If you can draw a vertical line somewhere that intersects the relation more than once, then it is not a function. And the reason why is the vertical line represents an input value, and we're checking to make sure that that input, that x value, has only one output, only one point of intersection. If it has multiple points of intersection, that's telling us in the relation, if we input that x value, we'd output multiple outputs. So our first example, there's our graph. Now notice I have a vertical line here. So if I move this vertical line, as I move it, determine how many points of intersection there are. Right, so if I stop it here, there's only one point of intersection here. If I keep moving the line, right, keep moving the line, only one point of intersection, one point of intersection, one point of intersection, one point of intersection. So it is a function, and our reasoning is the graph passes the vertical line test. Now, at home, you probably don't have this ability to drag a vertical line across your graph, so what you're going to do is draw in a few vertical lines. Okay, and as you draw them in, you're looking to see how many points of intersection there are. So taking my same vertical line to our next relation, so here I only have one point of intersection, but then right here we notice that there's 2 points of intersection with the vertical line. So what that tells us is if we input this x value, whatever it might be, maybe it's -3, then in this relation we output 2 different values for that input of -3. So this is not a function, and our reasoning does not pass the vertical line test. Perfect. 2 more graphs to look at. Determine if the following graphs represent functions. So this one looks like a set of steps, and we have open and closed points that we're going to have to pay attention to. So moving the line across, we have 1 point of intersection, 1 point of intersection, 1 point of intersection, and then we get right here. So now the question is that 2 points of intersection or is it only 1? Well, because this is an open point, that's really not part of the graph, right? It's just indicating that there's an open point there. Here's the closed point. So technically, this is only 1 point of intersection. So we can keep moving. We haven't failed the vertical line test yet. No, want to move the line. Okay, now we're moving our line. 1 point of intersection, 1 point of intersection, 1 point of intersection, 1 point till we get here. Same issue. We have an open point and a closed point. But again, the open point is technically not part of the graph. It's not a point on the graph. So we really only have one point of intersection again. Still good. Keep going, keep going, keep going. Made it to the end. Every vertical line only intersected once. So this is a function. Passes the vertical line test. So our next example, similar. Okay, so we start, draw a vertical line, 1 point of intersection, 1 point of intersection, 1 point of intersection, 1 point of intersection. We get here, same decision, but we have one open point, one closed point. Open point's not a part of the graph, so we really only have 1 point of intersection. So we can keep moving. Keep moving, keep moving, keep moving, keep moving. Still good, still only 1 point of intersection, till we get right here. Now both of those are closed points, which means they're both points on the graph, which means we have 2 points of intersection. So for this input, maybe it's x equals 2. So for the input of 2, we have 2 different outputs. So this is not a function. It does not pass, or it fails, does not pass the vertical line test. Now, we typically can only use the vertical line test as a justification or an explanation if we have a graph. Otherwise, we have to state something about the definition, the idea that one input maps to only one output, or it maps to multiple outputs. Now, which point, 1, 2, or -1, 8, when added to the table below, would keep it a function? So, one of those points is going to take an input and map it to 2 outputs. So let's look. If we look at our set of inputs, we have -3, we have -1, we have 0, we have 4, and we have 9. So if we look at -1, the output is 0, and the point they gave us, -1 maps to 8. So that wouldn't be a function, which means we'd want to add the point 1, 2. Okay, and the reason there would be every input would then map to only one output. We've written that definition quite a few times in this video. The input values for a relation are 5, 6, 7, 8, and the output values for a relation are -1, 0, 1. Write a set of ordered pairs using these values that represents, letter A relation that is a function. So we're going to have our set of ordered pairs. So we'll start with the input of 5. So input of 5, that's a weird 5, let's fix that. Input of 5, let's say the output is -1. And we'll take the input of 6, and we'll output 0. Input of 7 will output 1. And the input of 8, we have to use one of the outputs again, so let's use 0. So every input maps to only one output. So we have a relation that is a function. Now we need a relation that is not a function. So we'll start with the input of 5. And again, we'll map to -1. We'll take the input of 6 and map to 0. Input of 7 map to 1 still. 8 map to 0. So far it's the same as letter A. But then we'll take one of our input values, so let's take 6 again, and we'll output a different value. So in our set, 6 outputs 0, so now let's have 6 output -1. So there we've created a relation that is not a function. The input of 6 now maps to 2 different outputs. A lot of conceptual pieces. A lot of different presentations. Hey, we had mappings, we had tables, we had sets of ordered pairs, we had graphs, and the biggest idea that we have to come away from this video with is that the definition of a function is a relation where every input maps to only one output. That's the key idea. So now go and practice this concept so that you see more examples and you can get comfortable with defining a relation as either a function or not a function.